Okay, this video is about multiplications. We would multiply by completion and would apply this to the special case of multiplication by a sequence of nines. This is video number W4. This is video number 4 for a workshop, for 1 day workshop I'm planning to do. Let's continue. To revisit the example we did before, 75 times 25. We solved that by completion in the first video. So we did do some multiplications using by completion. Okay? So what did we do? This was the first video. Okay, if you want to look at video, this is the link. Okay, what did we do in that video? Do you recall that? We completed 100. Why did we do complete 100? Because 100 is a base number and multiplying by base number is very easy. Just add a couple of zeros to the right. Let's continue here. What did we do to complete 100? Do you know how to make 100 of 75? Do you still recall that? We did 75 equal 75 plus 25 minus 25. That's by addition and by subtraction. We combine the 75 and 25, 75 plus 25 to make a 100 and minus 25. So we say replace 75 by 100 minus 25. Okay, how do we find the number 25 to add and subtract? We use this sutra all from 9 and last from 10. All from 9 and last from 10 of 75. We are trying to convert 75 complete 100 of 75. So we do all from 9 and last from 10 of 75, which is 25. So we added and subtract 25. We found the number 25 from applying all from 9 and last from 10. By the way, this is a tens complement of 75. Continue. Let's continue here. All right, let's continue. So now we'll use that for multiply by sequence of nines. Okay, let's look at what sequence of nines are. Can we multiply by completion in multiplying with sequence of nines? Can we complete sequence of nines to make a base number? If we can, how do we do that? How would we complete a base number from a sequence of nines? Let's look at what sequence of nines look like. Is 9, 99, 999, 9,999, 99,999, and so on. Are not these numbers very close to natural base number? Is 9 close to base number, which is base number 10, 99 close to base number is 100, is 999 close to a base number is 1000, and so on. So these are very close to base numbers. In fact, the numbers above are close to this base number. 9 is close to 10, 99 to 100, 999 to 1000, 9,999 to 10,000, and 99,999 to 100,000. So we can complete a base number using the multipliers, which is sequence of nines. Okay? So we can use by completion to multiply by a sequence of nines. Let's continue. Okay, let's look at some examples of multiplication by 9. We would use by completion again here. Let's continue. Here's an example. 35 times 9. Okay. You know, we're going to complete 10 out of 9. You know how do we do that? So remember? Let's continue. So we'll replace 9 by 10 times 10 minus 1. It's 35 times 10 minus 1. Let's continue. Can you multiply 35 times 10? How about 35 times 1? So let's go multiply that out. Let's go to 35 times 10 is 350. and 35 times 1 is 35, and the symbol minus here and minus here. So 35 times 10 minus 1 is 350 minus 35, and that is equal to 350. Do you need some time to subtract that out? Okay, let's continue. Another example, 4886 times 9. Again, we will complete 10 from 9, and we will replace 9 by 10 minus 1 like we did before. Let's continue here. So that's equal to 4886 times parenthesis 10 minus 1 parenthesis close. Let's continue here and multiply that out. 4886 times 10 is 48860, and 4886 minus 1 is minus 4886. Okay, let's subtract this thing out, and the answer is 43974. That means 4886 times 9 is 43974. Now we would take an example of by multiplication by 99. We will use the by completion again. Let's take example 1133 times 99. We complete 100 out of 99, and in doing so we will replace 99 by 100 minus 1. So 1133 times 100 is 113300. 1133 minus 1 is minus 1133. Okay, let's subtract this number. So answer is 112167. So 1133 times 99 is 112167. Another example, 2359 times 99. 2359 times 99. We will complete 100 from 99, which is you replace 99 by 100 minus 1. Let us continue here. So we just replace that. 99 becomes parenthesis 100 minus 1 and parenthesis. So let's continue. 2359 times 100 is 235900. 2359 times minus 1 is minus 2359. So that's equal to 233541. So 2359 times 99 is 23351. Okay, let us continue. Now we'll do some examples of multiplication by 999. Okay, let's continue here. Example 39617 times 999. We would complete 1000 out of 999, and we will replace 999 by parenthesis 1000 minus 1 parenthesis close. Let's continue here. So that's equal to 39617 as it is times 999 replaced by 1000 minus 1. Okay, so that let's multiply that out. 39617 times 1000, which is 39617 and 3 zeros, and 39617 times minus 1 is minus 39617. Now let's subtract it out, and there comes 395383. Need any time to subtract it out? Let's continue with the next example, please. It's 16391 times 999. Again, we replaced 999 by 1000 minus 1. What we just did is completing 1000 out of 999. Now we can multiply that. 16391 times 1000 is 16391,000. Okay, and 16391 times minus 1 is minus 16391. Let's continue and subtract this out. It becomes 16374609. That means 16391 times 999 is 16374609. You can do some exercises now. Okay, let's try that. A few examples for multiplication by 9. A couple of examples, some examples by 99, 6888 times 99, 2194 times 99, and some more. And a few examples for by multiplication by 999, 97941 times 999, and some more. Okay, you can do one or two of these as you feel comfortable. Okay? We will wait and start over after you are done. Okay, let's continue. We would have discuss some cases for this multiplication. In Vedic math, we always try to find shortcuts to the answer. Our mantra is short and sweet, one line mental solution. Okay? So we try to find an answer without really working out the problem. So in my humble opinion, you also need to know how to solve the problem. So we have already shown you how to solve the problem, okay, by completion, and now we would look into a shortcuts in some cases. Our classification is by relative length of the operands. So cases here are are based on relative length of the operands. In multiplication, the operands are multiplicand and multiplier. Case for multiplication continue. Let's continue that discussion here. This was the from previous page, previous slide. The cases are number of digits in both operands are equal. That's a very common case, and that's we would use more frequently. Okay? Number of nines in multiplier are more. There are more nines than the digits in multiplicand. Number of digits in multiplicand are more. Length of the multiplicand is larger than the length of the multiplier. Multiplier is a sequence of nines. Let's continue here. For the first two cases, we have shortcuts given by sutras. For the third case, just use the workout studied earlier. That's my opinion. Okay, books try to put words around that case too, but I find those words confusing. Okay? Let us continue. Okay, let's take off with the case where the lengths do match. Let's continue. Example is 347999. Multiplicand is 347, multiplier is 999. There are 3 digits in multiplicand and 3 in multiplier. Okay, let us see, continue here. So we would complete 1000 from here, which and then replace 999 by parentheses 1000 minus 1 parentheses closed. So it said we replace 347 times 999 by 347 times parentheses 1000 minus 1 parentheses closed. Okay, so this is an equivalent problem to the original problem. This is my original problem, this is my equivalent problem. Let us continue here. So that on the left we have 347 followed by 3 zeros. Okay, 347 and 3 zeros. 347 times 3000 minus 347. Okay, so we write a minus 347 on the next line here. Let's continue here. To the right of this bar here, it's all from 9 and less from 10 of 347. So we're going to right of this bar, it's going to be all from 9 and less from 10 of 347. That is 653. Okay? All from 9. Okay. 3 from 9 is a 6. 4 from 9 is a 5, and 7, this last one from 10 is a 3. So on the right side of this bar, I have a 653. Okay. On the left side of this bar here, I get 1 less than before. 1 less than before of 347, which is 346. So on the left, I have 346. On the right, I have a 653. Okay. So the product is 347 times 999 is 346653. Okay. Let's con let's continue this same case example again. Okay. Let's do 347 times 9999 is 346653, which is from the previous slide. Okay. In case of matching lengths, on left we have 1 less than before of the multiplicand. Multiplicand here, so it's 346 is 1 less than 347. On the right we have all from 9 and last from 10 of multiplicand. 653 is all from 9 of and last from 10 of 347. 3 from 9 is a 6, 4 from 9 is a 5, and 7, the last one from 10 is a 3. Okay, let's continue here. Observations. Left is 346, right is 653. We just computed that one here. Then let's go compute 346 plus 653 is 999. Left plus right is 999. Sequence of nines, that's what we're trying to multiply by. Okay. Okay. The two parts are nines complement of each other. That means 346 and 653 are nines complement. You get 653 from 346 by applying R from 9. You get an 653 from 346 by applying R from 9, and 346 from 653 also by applying R from 9. Okay, let's continue here. Okay, let's continue with same example here. Again, we note 1000 minus 999 is 1000 minus 1, and which is equal 1000 plus negative 1. I use the underscore here to denote a negative number here. So which is 100 and a negative 1. Okay, let's continue here. Expression become 347 times 100 negative 1. Okay, and that is 347 positive and 347 negative. Okay, if you multiply them together, so this uh, on the right side you get 347 times negative 1, which is 347, and that this 3 and 4 comes in same place where zeros are. Okay, and then 347 times 1 is 347. Or you can say 347 times 1000 is 347, and 347 minus 1 is underscore 347. Okay, and when we resolve the negative numbers here, I got the same 346. Let's do some more examples here. Matching lengths. 1714 times 9999. Okay, on left I have 1713, which is 1 less than before. Around right I have it 8286, which is all from 9 and last from 10 of 1714, or all from 9 of 1713. Okay, let's continue here. That means 1714 times 9999 is 1713, 8286. Another example here. Let's see how we use these in recurring numbers. 1 over, if I need to compute 1 over 7, I would do, on first step, I will multiply both the numerator and denominator by 143. That is by multiplication and division by 143. Okay. How I got number 143? It's in a subsutra, but when we do a section on recurring numbers, I will show you how we got that. Okay, let's. So that gave me 143 over 1001. If you need time to multiply 7 over 143, go ahead. I would give you some time. So check it out. 7 times 143 is 1001. On the next step, I'll multiply and divide by 999. 9. So this is where we use multiplication by a sequence of nines here in recurring numbers. So 143 times 9999 is 1001 times 9999 divided by. So 999 is 1 less than 1000 and 1001 is 1 more than 1000. So it's like 1000 plus 1 times 1000 minus 1, which is like a plus b times a minus b, and which is a squared minus b squared. But here you can say 1000, same thing, 1000 plus 1 is 1000 plus 1, and you can multiply that out by 999. Okay, let's continue here. So on the numerator, I have a 1 less than before on left and all from 9 and last from 10 on right, which come 142,857. In the denominator, I got 999, 999, 6 nines in the denominator and 6 digits in the numerator. Yes, if you multiply this thing out, 999 times 1000 is 999,000 plus 1, 999, so that gives 99999. And 6 digits on numerator and 6 nines in denominator is a common fraction equivalent of a recurring number, which recurring number is 142,857. So that means 1 over 7 is equal to 0.142857 recurring. Okay, let us continue here, and that's common fraction of. Let's do rules for case number 2. So case 2 is multiplier has a higher length, larger length than the multiplicand does. So we have more nines than the digits in the multiplicand. Okay. Number of digits in multiplicand is less than number of nines in the multiplier. That's the case 2 here. In this case, prepend multiplicand by adding zeros to the left. Okay. So we'll look at a recurring number example here again. So for 1 over 13, first we do multiply and divide by 77. So 1 over 13, 1 times 77 and divided by 13 times 77. Okay, let's continue here. So that's equal 77, 1 and divided by 1001. We did that. Okay, you multiply that out. 13 times 77 is 1001. Okay, after that we multiply and divide by 9999 just like we did before. 999,999. This one we know in the denominator comes in a sequence of 6 nines. Okay, let's look at what the numerator looks like. So in numerator it's 2 digits of multiplicand and 3 digits of multiplier. So we prepend a 0 here to make the lengths match. Okay, so in numerator we have a 1 less than before on the left and all from 9 and last from 10 on the right. Okay, so this is a common fraction for a recurring number. A recurring number is 0.076,923. Okay, that means 1 over 13 is equal to 0.076923 recurring. We just computed a recurring number equivalent of 1 over 13. Okay, so we use these multiplication by 9 sequence of nines in computing recurring numbers and some other astronomy, I believe they use examples. Okay. Let's do some examples. Here we consider examples from the book Figuring the Joy of Numbers by Shakuntala Devi. Okay. Okay. The book does not explain how the author of the book gets the results. However, you will learn both the results and how to solve these problems. Okay. In the book, it says 33 times 33 is 1089, and that's from the book. Let's see if we would use this multiplication by 9s here to compute 33 times 33. Let's see how do we replace this problem by an equivalent problem. Okay, let's continue. So 33 times 33 is 11 times 3 and times 11 times 3. 33 is 11 times 3. Okay, let's continue here. So that means what? 11 times 11 times 9. Okay, which is 11 times 99, and now it's in the same format that we have been doing that before, which is a 11 times 99, two nines, two ones, two digits. Okay, that means one less than before, 10, and all from 9 and last from 10 on the right, 89. Okay, okay, so that we did already. Okay, let's do next one here. 333 times 333 means 111 times 999, which is one less than before, 110, and all from 9 less from 10 of 111 is 889. Okay. 3333 times 333 is 4 threes times 4 threes is 4 ones times 4 nines, and that's 110, one less than before, and 8889, which is all from 9 and last from 10. 5 threes now. 3 times 3, 33,333. It's equal to 11,111 times 9, 9,999, which is equal to 1 less than before of 11,111, 11,110. Okay, and all from 9 and last from 10 of 11111. 88889. Okay, okay, let's see next one. 6 threes here. 3 times 3 times 3, okay, which is 111,111 times 999,999. Okay, which is equal to 111,110, which is one less than before, and 888,889 is all from 9 and last from 10 of 111,111. Okay? And so so on. So you can continue it at least. Uh, you see. Let's go to examples here. Some more examples. So here's another example from same book. 1, 2, 3, 4, 5, 6, 7, 9 times 999, 999, 999. Okay, and the book notes that that's equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, this is center of symmetry, and left part is a mirror image of the right part. Okay, let's continue here. And n is a perfect square. So book notes that this multiplication is equal to that, and this number is a perfect square. Okay, let's see what's going on in here. Okay, first inside number 1, 1, 2, 3, 4, 5, 6, 7, 9 times 9, 9, 9, 9, 9, 9, 9, 9, 9. 8 digits here and 9 digits here, 9 nines. Okay, so we would add a 0, prepare 0 to the left of the multiplicand to match the length. Let's continue here. So I just did add a 0 here. So multiplicand has 9 digits and multiplier has 9 nines. Okay, so what we will result is 1 less than before on the left, and R from 9 and last from 10 on the right. Okay, so this is 1 less than before, 0, 1, 2, 3, 4, 5, 6, 7, and 1 less than 8. Okay, here is R from 9 and last from 10. Okay, from 9 is a 9, from 9 as 8, from 9 there's a 7, from 9 there's a 6, from 9 as a 5, from 9 of that is 4, from 9 of that is 3, from 9 of that is a 2, last one, from 10. 9 from 10 is a 1. So is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 7, 6, 5, 4, 3, 2, 1. Just like this one here. So we just computed that multiplication using the multiplication we just studied. Okay, let's continue here. Now inside number 2. Now we have to also prove that it's a perfect square. Okay, so 1, 2, 3, 4, 5, 6, 7, 9 times 9, 9, 9, and 9, 9, 9, 9, 9, 9. Okay, which is equal to 1, 2, 3, 4, 5, 6, 7, 9 times. I'm going to extract out 9 here, a factor. 9 times 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay. Now you multiply the 1, 2, 3, 4, 5, 6, 7, 9 by 9. Okay. You should get 1, 1, 1, 1, 1, 1, 1, 1, 1 times 1, 1, 1, 1, 1, 1, 1, 1, 1. Does it tell you this is a perfect square now? It's now perfect square, okay? And the answer is 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 8, 7, 6, 5, 4, 3, 2, 1. If you need to multiply these out and try out, you would get to this answer here, okay? So this is the observations the book made, and this is how you solve these. First multiply that one way to get this answer here, then multiply another way to make sure that's a perfect square. It's a perfect square of 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, let us continue here. The square of 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, let us continue. Now some problems of multiplication of by sequence of nines. Okay, try these. 3, 7, 6, 0, 7 times 9, 9, 9, 9, 9, 9, and some more. Let's look at some references here. There's a video by completion, and that's my location there. Then multiplication by sequence of nines, we have another video doing sequence of nines and discussing some other methods here in the math. And the book Figuring Joy of Numbers by Shakuntala Devi. We have used some of the examples from her book. Okay, that's it. Okay, that's all.